Okay, so what's happening there is something called entropy. Entropy is not the same as spontaneous, but it is, well, you'll see how they're related in a minute, but entropy has to do with disorder. So if you think back to those gas molecules, if they're all packed on one side, that's more ordered. The system wants to go to become more disordered, and so those gas molecules are going to disperse. So that's tending toward disorder. That's a measure of entropy. Same thing with the heat. It's very hot on one molecule, on one block, and then the heat will transfer to the other block, and so that is a measure of entropy. So this is a factor that is also important besides the heat of the reaction. Entropy is a thermodynamic quantity, and like I said, it's a measure of randomness or disorder. The units for entropy is joules per Kelvin, and I just want to point that out. That's the units that will be in the back of Appendix G. And why I want to point it out is because for some odd reason, entropy is always in terms of joules per Kelvin. So you'll see in a minute, it's going to be multiplied by temperature, but joules, whereas delta H is in kilojoules. So that's going to become important to be aware of. Just be aware of your units. So again, another way to think of entropy is just how dispersed is the system about different possible ways. So if the energy is concentrated, then entropy is low. It's very ordered. If that energy is dispersed or spread out, then entropy is high. It's more disordered. You can actually look up a measurement. If you take the same amount of liquid water or ice, then the entropy of water is higher. It's more random. Water is more random than ice. So entropy, and then gas, of course, would be even higher because gas is more random than liquid. Now, why is water liquid more random? Well, we know the ice crystals are more regular. They're fixed. They're held together in a more regular pattern. The molecules can still move, but they're still much more restricted than water molecules in a liquid. And then, of course, if you go to the gas, the water molecules are even less restricted. And so, again, entropy increases. So sometimes you'll hear the term free, no, not free energy, but, units of freedom or degrees of freedom. The more that something can move, the more freedom it has, the more entropy it has. So exactly what I just said here. So the entropy of a substance will increase as it goes from an ordered solid to a liquid to a gas. Entropy increases if you go in the other direction. Entropy decreases. Interestingly, entropy is a positive number, and so if entropy increases, delta S is positive, and that's also a difference from delta H. Remember, delta H, exothermic is negative, endothermic is positive, but in entropy, positive is more disorder, negative is less disorder. Less disorder, more order. Okay, so processes in which disorder increases will tend to occur spontaneously. Again, it's not absolute, but they do tend to do that. So, for example, when the ice melts, what's happening? The molecules become less rigid, they can move more freely, and so liquid is more random. So we know that ice melting is a process that occurs spontaneously. Now, you might realize that it depends on the temperature. If I have ice at negative 10 degrees, it's not going to spontaneously become liquid. And so we'll see where temperature comes into play in a little while. But if you just have water, ice at room temperature, it will spontaneously become liquid. If you dissolve salt in water, that is the entropy increases. The salt generally, unless you put way too much, the salt doesn't sit at the bottom undissolved. It will dissolve in the water and become more random. The salt crystals move away from each other and separate and mix with the water, and so that is an increase in entropy. If you, like we saw a few slides ago, if you have gas at high pressure and you open the stopcock and the gas is allowed to move into an area of lower pressure, the entropy will increase. It's going to occur spontaneously. If you have a balloon that's blown up and you open you untie the knot, the air is going to come out. It's going to be spontaneous. So in each case, energy has been dispersed or spread out. So the entropy of the system plus the surroundings has increased. So entropy is also a state function, just like enthalpy. So again, it doesn't depend on the path, it only depends on the final state and the initial state. And just like delta H, delta S is the entropy of the final state minus the entropy of the initial state. The delta H we look at the delta H because those are delta H of formation for molecules, but S's are not delta. So the delta S is just for the overall reaction, and we look up entropy values. So again, if delta S is positive, that means that the final state is more disordered than the initial state. So that means it's an increase in entropy, more disorder. And if delta S is negative, that means the final state is more ordered or less random, and so that is a decrease in entropy. So the second law of thermodynamics says that the total entropy of a system and its surroundings always increases for a spontaneous process. So that's kind of an interesting one and can get really deep. So we're just going to, again, stay at the surface. So if you look at this reaction, you say, okay, the entropy of the universe, which is everything, so the entropy of everything. And remember, we've already defined, so like we've defined the system and the surroundings. And so together, the system and the surroundings are the universe. And so the system, the entropy, the delta S of the universe is just the delta S of the system and the delta S of the surrounding. Because energy is always dispersed in a spontaneous reaction, then the delta S of the system is not conserved, or delta S overall is not conserved, because the delta S is continuously increasing. And so the universe, this is where we say the universe is tending toward disorder. So that kind of supports the Big Bang theory that we started with complete order, and ever since then we've been tending toward disorder. And so that's the second law of thermodynamics. And it goes a little bit deeper than this, and I haven't, it would be in a higher level chemistry class than this one. But let's look at just some examples. So like this. So let's say you straighten up your desk. Okay, it is more ordered than it was before. So delta S is negative because the system, the delta S for the system has decreased. It has become more ordered, less disordered. But if you're anything like me, what happens when you clean your desk? First of all, you have to use your own energy because you're going to have to metabolize food. You're going to generate heat. You're going to make like me, make a mess. Usually I carry everything that was on my desk over to another place and make a complete mess over there. So the entropy of the surroundings are always increasing. So overall entropy is increasing, even if one location entropy decreases for just one small thing. But the important thing here, this is more helpful to remember. The first law of thermodynamics is about total quantity of energy, how much energy is being transferred. The second law of thermodynamics is more about the quality of the energy. That's kind of where we want to try to conserve energy, and so the second law of thermodynamics kind of comes into play there. So as heat energy is transformed or transferred to entropy, so as energy becomes entropy, less of it can be used, more of it's wasted, and so that's more about the quality of energy. And sort of in a similar way, we can look at, let's look at the oxidation of iron. So this is, if you have an iron nail sitting outside in the rain and it's reacting with oxygen to produce rust. If you look at just the system, the delta S for the system is negative. Why is that? We're going from 7 molecules or atoms to 2. We're going from smaller atoms to something that looks much more complicated. So, and also we'll see in just a minute, we tend to look at gas molecules. We're going from 3 gas molecules to no gas molecules. So all these things sort of imply that that the system is becoming more ordered, is negative. But it turns out in this case that the reaction is exothermic, heat's being released. And so overall, so the entropy of the surroundings is becoming, the entropy of the surroundings is increasing because the heat is being involved, thermal motion of the molecules is increasing, and so overall entropy increases. The main thing you want to remember then is that no process that produces order in a system can proceed without producing an equal or greater disorder in its surroundings. So again, you might think more about the cleaning your desk. You can order one little part of it, but overall, the whole universe is increasing in entropy. So that's the second law of thermodynamics. We can reinstate it in a way that only refers to the system that we're interested in. So if we have a spontaneous process that occurs in a system that is in thermal contact with its surroundings, so for example, a chemical reaction in a flask is in contact with its surroundings. As the chemical reaction takes place, entropy is produced, and at the same time, the heat might flow into or out of the system as a result of this thermal contact. And so entropy is produced because because of the spontaneous reaction. The heat flow is also an entropy change because it's a dispersion of energy. So you can think about the heat leaves and the molecules start outside the system start moving faster. So that's an increase, that's a dispersal of energy, that's an increase in entropy in the surroundings. And so the entropy change is associated with the heat and with the temperature because it's a temperature change. So again, this is kind of the nitty-gritty equation development phase, but this net change in entropy of just, again, keep in mind, of the system, where S is the sum of the entropy created during the spontaneous process and the change in entropy associated with the heat flow. So delta S for any spontaneous process is equal to the entropy created plus the heat divided by the absolute temperature. So I'm not totally sure I even understand the process of this, but we'll just take it as it says. This is the delta S is defined as the entropy created plus the heat of the reaction divided by the absolute temperature. Normally, the quantity of entropy created cannot be directly measured, and it's in the surroundings, and so it's not something that measured. So what we do is rearrange that equation so because it's the delta S is equal to Q over T plus something, then we know that delta S is going to be greater than Q over T. And this is probably the better equation to remember. So for a spontaneous process, entropy will be greater than the heat of the reaction divided by the absolute temperature of the reaction. So this is just a restatement of the second law. For a spontaneous process, the change in entropy of the system is greater than the heat divided by the absolute temperature. So spontaneous reaction, again, keep that in mind, it's a spontaneous reaction. The change in entropy, delta S, is greater than Q divided by the temperature that's given to you. Now, if there's a phase transition happening, like ice melting or liquid vaporizing or vice versa, what's happening is those processes are staying at equilibrium or very near equilibrium. And so in those cases, no significant amount of entropy is created. And so we say at equilibrium, delta S equals Q over T. So all of the entropy that is produced has to do from just the heat of the reaction divided by T. So that's at equilibrium. The previous one was a spontaneous reaction. Again, same thing with other phase changes. Vaporization or sublimation. Those are all equilibrium, so that equation holds. Okay, so let's just look at an easy example. If the heat of vaporization, so delta H of vaporization, again, that's the amount of heat required to vaporize liquid to gas. So the heat of vaporization for carbon tetrachloride at 25 degrees is 43 kilojoules per mole. So if 1 mole of liquid carbon tetrachloride has an entropy of 214 joules, so that's just what it happens to be. And these are really hard to measure, but we're just assuming. What if the has an entropy of 214 joules per kilogram? What is the entropy of 1 mole of vapor at this temperature? So remember, we're talking about an equilibrium. Delta S equals Q over absolute temperature. So that's at equilibrium. So it absorbs 43 kilojoules per mole. So remember, that's delta H. 25 degrees, so the entropy change, delta S, is the delta H of vaporization. And since entropy is always in joules per Kelvin, that's why it was converted to joules, divided by Kelvin. So this is 144 joules per Kelvin per mole for 1 mole. So we can find the delta S only if it's a system at equilibrium. Okay, so we just found delta S, and remember, delta S is the change in enthalpy, and that was 144 kilojoules. I'm sorry, joules per Kelvin. And what they're telling us, though, is that the entropy of the liquid is 214, so they're asking you what is the entropy of the vapor. So remember, delta S let's write it over here. Delta S is the entropy of the final minus entropy of the initial. Well, it's initially liquid, so it's 214 is the liquid. What's the final? Well, we don't know. That's what we're trying to find. What is the entropy of the vapor? But we know that the delta S is 144 joules per Kelvin. Joules per Kelvin. So the final, the vapor, the moles of vapor, the entropy of the vapor is going to be 144 plus 214. So we're going to add 214 to both sides. And so the entropy of the vapor is 358 joules. So it increased, the delta S we found was 144, so it's 144 more than what we started with. All right, then our third law of thermodynamics just states that a substance that is perfectly crystalline at 0 Kelvin has an entropy of 0. So that's why we define absolute zero. Absolute zero means that whatever it is has an entropy of 0, meaning it's not moving at all. It has no dispersion of energy. It is totally frozen, crystalline, 0. There is no movement at all. As soon as you move the temperature even just a tenth of a degree, the substance becomes more disordered because it absorbs heat, starts moving, so that's more disorder. So they're saying 0 Kelvin is absolute 0. That's when entropy is totally 0. And so then the entropy of a substance is determined by measuring how much heat is required to change its temperature. So what is the entropy per degree Kelvin? So that's what the heat of reaction is. All right, so we can, it's sort of like we said before, we can also find the this delta S for any reaction by looking up the table in Appendix G. So you may have seen them before when we were looking up delta H values. They're in Appendix G, and there were 2 other columns, and we said we'll get to those. Well, now's the time that we're going to get to them. So we can look up the absolute entropy for any compound at standard state. So the little 0 means standard state, which is 1 atmosphere pressure and 0 degrees Celsius. 25 degrees Celsius. Standard state implies 25 degrees Celsius, 1 atmosphere pressure. And if we have a solution, it's 1 molar solution. And then remember that delta H, if you had a pure element, the delta H was 0. Well, that's not true for entropy because everything has entropy if it's above 0 degrees Celsius or Kelvin. So elements do have non-zero values, so make sure and look them up. So we use the symbol S rather than delta S for standard entropies because they originate from the third law, meaning that it doesn't matter if it's an element or a compound or anything, it's going to have some entropy. So we don't use delta S, we just use S. All right, but like before, we can look up the values for entropy. We can find the delta S for any reaction, and it is the entropy of the products times their coefficient minus the entropy of the reactants times their coefficient. So again, the sum. So like I said, we just looked at this a few minutes ago. Even without knowing the values, we can sometimes predict the sign of delta S, but we can also always calculate it using Appendix G. So let's first do some more predictions. Entropy usually increases in the following situations. If molecules are broken down into 2 or more smaller molecules, then we know that entropy is positive. It's tending to increase. If a reaction has an increase in the number of moles of gas, that tends to be a positive entropy. And if something goes from a solid to a liquid, or a liquid to a gas, or anything that's becoming more than delta S should be positive. So oftentimes you can predict if your answer is right by kind of looking at the overall reaction. So let's see what's happening. Is delta S positive or negative in these situations? Okay, if H2O liquid becomes a gas, all right, that's becoming more random, so that's an increase in entropy. Delta S is positive. Silver ions and chloride ions precipitate to form silver chloride solid. So you can imagine they're swimming around in solution, and then now they're a solid, and so that's a decrease in entropy. It's becoming more ordered, so delta S is negative. What about iron reacting? We've already talked about this one. Iron reacting with oxygen to give us rust. Well, we can look at it a couple of different ways. There's 7 total molecules going to 2 molecules, so that's a decrease in entropy. They're becoming you're going from small particles like 1 molecule or 1 atom to a much more complicated molecule, so that's also an increase in order or a decrease in entropy. And usually what we look at is the gas molecule, so we're going from 3 gas molecules to 0 gas molecules, so that's also a decrease in entropy, so delta S is 0. Okay. This just kind of gives you an idea. So this is table 16.2 in your book, and there's also, remember, Appendix G has a lot of these values. So these are just some examples you can, and kind of what I'm looking at is, look at the gases. The gases tend to have much higher entropy than the liquids, especially if they're the same compound, but overall the gases tend to be higher numbers. And so anyway, these are just values that you can look up. These are standard values. All right, so now we can use those values either from that table or from Appendix G for the other values. So let's calculate the delta S for this reaction in which urea is formed from ammonia and carbon dioxide. If you were to look up in the appendix the entropy for NH2CO NH2, you wouldn't be able to find it, but the problem is giving it to you. It's telling you it's 174 joules per mole Kelvin, and then we're going to look up the other values. First, before we do the calculation, let's kind of look at it. You can see that we're going from 3 gas molecules to 0 gas molecules. So we expect that the delta G, that is becoming, and we're getting a much more complicated molecule on the right-hand side, and we're getting liquids in aqueous solutions. So we expect that our delta S should be negative, that it's becoming more ordered. But let's look up the values and see. So you're going to look up these values in Appendix G. And again, it's similar to what we did for delta H. So I have looked them up for you and found them. So the entropy for NH3 gas is 192.8 joules per Kelvin. CO2 is 213.8. The urea was given to you 174. Actually, that should have a 0.0. And the H2O is 69.9. So sometimes I'll put them on the bottom, and remember that you have to multiply by the coefficient. So it's always products, 174 plus 69.9, add those together, minus the reactants, multiplied by their coefficient. And so we can use the summation law. And you can see that we have the products, 174 plus 69.9, minus the reactants, 2 times 192.8 plus 213.8. And so be careful with your signs. It's really easy to make mathematical mistakes. So this is negative 355 joules per Kelvin. And so as we predicted, it's becoming more ordered, and delta S is negative. And so this is how you would do the delta S values, just the same as we did the delta H, and you find the values in the same appendix in the back of the book. Okay, so now we're going to relate our entropy and our enthalpy to spontaneity. So we've already kind of mentioned spontaneity, and things we see that things tend to be spontaneous, and we know in general that something that's becoming more disordered is more spontaneous, like those gas molecules being in one flask and then spontaneously moving over to the other side, expanding, or hot temperature just spontaneously moving to a colder area. But not all things that are more disordered are spontaneous. We'll see an example. I think we saw an example earlier, and we'll see another example. The same thing as we tend to think about things that are exothermic, that give off heat, give off energy, as being spontaneous, but not always. And so now we're going to look at the relationship between entropy, enthalpy, and spontaneity. So remember that heat at constant pressure is equal to the enthalpy, delta H. And from the second law of thermodynamics, we found out that delta S is greater than delta H over T for a spontaneous reaction at constant temperature and pressure. So now we can see how, if we rearrange this equation, we get this equation that if you take delta H minus T delta S, it should be less than 0 for a spontaneous reaction. So this implies that the combination of the enthalpy and the entropy, according to this equation, must be negative for a reaction to be spontaneous. So it's not necessarily that delta H has to be exothermic. It's not necessarily that delta S has to be positive, becoming more spontaneous, but it depends on the balance between them. And then if delta H minus T delta S is positive, then the reaction is non-spontaneous as written, but spontaneous in the reverse reaction. If delta H minus T delta S equals 0, the reaction is at equilibrium.